Okay, so we will look at this side of the paper, Major 20, variant 3. Okay, the first question here is actually about the roots of the polynomial. So the first question here, they actually gave us, okay, the cubic equation here. And here, the first one here is actually find the cubic equation, which we have got these roots, alpha to the power negative 1 and so on. So we know this is like, we need to let like the new variable, say the y, to be the new root there. And then we actually make the new root as the subject here. Okay, so after that, then we will actually have to sub in those 1 over y into the x before that, and we just have to tidy up from there. Okay, so once we actually tidy up, this is the value. Okay, so in the part B here, right? So find the value of the a power negative 2 plus a b power negative 2 and so on. So for this, right, okay, there are two different ways that we could actually deal with that. Of course, this, we can actually change it to like S3 plus a 3, S2 and so on, right? And we can actually like try to find what is actually the S negative 2. This is like an S negative 2 from there. Okay, so from here we can find the S negative 2. But it's actually quite a bit of work for us to do. Okay, in fact, this question only has got like 2 marks. So how do we actually look at it is that this expression here is just like the sum of squares of the roots of this. Okay, this is like the sum of squares of the roots of like this roots here. So the alpha power negative 1, beta power negative 1, and gamma power negative 1, they are the root from the new equation. So this is just like finding the sum of squares of the roots from the new equation there. Okay, so here we just have to, for me, I actually try to avoid confusion. So whereby I actually let the new roots all to be like the capital A, B, and C to avoid a bit of the confusion there. All right. So what we have, after that is, okay, we could actually find the sum of squares of the roots, which is like all these, okay? It's the sum of alpha, which is, in this case, the sum of A. So sum of A squared minus 2 sum of the AB. So for this, we are actually getting the value here, okay? So this is why this question only has the 2 marks, okay? So it's to use the new equation to find this value here. So from there, okay, the part C is to find the sum of the roots to the power of negative 3. So we can actually look at it as like an Sn already because the power there is getting a bit large. So we can make this Sn, okay, to be like the alpha power negative 1, beta power negative 1, and gamma power negative 1 to the power of the n. We add them together. So what we actually can obtain is that, okay, again, these roots, okay, are already roots from the equation that we have for this one. Okay, so just change all the coefficients there, okay, and the y there to become like Sns. So in this case, for all the Sns, right, we are trying to find the S3 for this case. This is our S3, and it actually depends on the S2, S1, and the S0. S2, we already found it in the part B. S1 can easily get from the coefficient, okay, for the equation here. S1, it is just like the negative B over A, so it's a negative 5. So for negative 5, okay, for the S1, S0 is just a 3. So from there, we just have to evaluate this. Okay, then we can get the value for this first question here already, right? So whereas, okay, for the second question, it's a bit about the induction. So, okay, we've got this sequence. Given that we have got the U1 is 1 and also the UN plus 1 is a 2 UN plus 1. So basically, this is something that is not very unusual for us to actually prove. So this is what we want to prove. The UN is 2 power n minus 1. Okay, so we need to let PM to be the UN, okay, 2 power n minus 1. And from there, okay, when the n is equals to 1, so we need to prove that the U1 is actually taking the 1, which we can actually check it against this U1 here. So we can actually get a 1 here. So the P1 here is true. So after that, it's the same thing. Assume the PK is true for some k is greater or equals to 1. And after that, right, we have got the PK plus 1. So the PK plus 1 here is to prove by using the UK plus 1. So the UK plus 1, we are first using the relationship here first. Okay, so the UK plus 1 is actually 2 times the UK plus 1. And from what we have actually assumed for the UK, we actually sub in here, okay, which is 2 power k minus 1. So after that, right, okay, what we actually do is that we just have to tidy out a little bit by expanding, tidy out. So this is what we actually can prove. So by induction, we can actually prove this Pn is true. Okay, so this is something which is not so unusual, yeah. Okay, the part 2 here is a bit of a special stuff here. Okay, deduce that U2n is divisible by the UN for the n is greater or equals to 1 here. So our aim here is to try to like express. Okay, if we say that 6 is divisible by 3, let's say, so we're actually trying to write it as a factor of the 3 like that. So this is what we do here, the similar thing. If you want to prove that the U2n is divisible by the UN, we have to express the U2n until we get like UN multiplied by something else. Okay, that's how we can actually prove it. So what we can actually look at from there is that, okay, this is the expression for the U2n, okay, which is a 2 power 2n minus 1. And this we can actually look at it as like a squared minus b squared form. So this is like a 2n with a square, okay? And then the 1 here is actually like the 1 square itself. So we can actually like factorize it into a plus b and then a minus b. So the good thing that we actually like factorize it is the a minus b here. This is actually our un. Okay, so the U2n can be actually expressed as something which is in terms of like the un. And also there is one thing that we need to sort of like explain a little bit is 2n plus 1. So we need to have like this 2 power n plus 1 is an integer. If it is not an integer, means it could be, if it is a fraction, it means that the U2n is not divisible by the un already, yeah? Because divided, we still have got some, like a fraction there, so which is not right. Okay, we need to also like mention about something like this here. 2n plus 1 is an integer, just to be clear about that proving. Okay, so after that, we can actually like conclude that U2n is divisible by the un. Okay, so this is some special questions from that. Okay, next. So this is Sn. Okay, so for this Sn here, we need to show that the Sn is given by this result here. So basically, we need to change the terms that we have there, right, into the summation symbol, okay, the sigma notation. So from the Sn, how do we actually cheat a little bit is that we usually look at the last term here. So we just need to change the n there to the r for the last term there. So we can actually form our sum already. Okay, so this is how we can actually obtain the summation notation. Okay, the sigma notation. If we are still not very confirmed or sure about it, we could always sub in the values and check. Okay, so let's say we can sub in the first few values here and we could actually check that. So it's true, okay, this statement or this formula is actually correct. So before we can actually apply those formulas from the MF19, from here we just need to expand, okay? Expand everything. Then after that is to actually like split the terms, everything there, right? And then we just apply sum of the r squared, sum of the r, and then this is like an n. Okay, so the work that we need to do afterward is about like, okay, we tidy up the constants, everything first. And here what we can do is we have to factorize out some common terms. So not much. The common terms is like n. And we also need to factorize out some fractions, which allows us to actually have like a nice value from that. So you could factorize 1/3 out as well. Okay, but for this case here, I'm trying to factorize out 4/3. So it actually gives us like 2, 6, and also 3, which is without any fractions there. Okay, so basically inside that, we just have to expand and tidy up. So this is the final result that we actually get, what the question actually wants us to actually prove here. Okay, so this is our part A. As we have in the part B, express n over Sn in partial fractions. And we have got to find the n over Sn in terms of the capital N. So basically, n over Sn is actually like this expression, and we know that it can be split into partial fractions like this. Okay, so this is our partial fraction. Okay, so from there, okay, we just need to sum this partial fraction here. So we have got this partial fraction, right? So it has got the coefficient of like the 3/8. So it depends whether we want to keep the 3/8 inside the summation, or for my case, I'm trying to factorize it because it's easier for us to actually check the cancellation later. So once we factorize out the 3/8, right, we are just working with this. okay, 1 over 2n minus 1, and also the 1 over 2n plus 1 there. So after that is to sum in the values, okay? This is when n equals to 1, n equals to 2, and so on. This is n is equals to n minus 1, this is equals to n is equals to n here. Okay, so here we can sort of see a bit of the cancellation already. So you can actually do the cancellation there, and you can actually write down the result straight away here. Okay, so this is a result for us using the method of differences. Okay, so not much for this. Okay, and then for the last part here is, did you use the value? So they just want to look at the value. It's a 1-mark question. So basically, that is when we have the capital N approaches infinity. So in our sum there, this term here will actually approach a 0. So overall, okay, after that, it will actually gives us the sum here is actually a 3 over 8. Okay. Okay, next question. We have got a matrix A, right? Which is given by this form. So that A is, show that A is non-singular. Non-singular in the sense that this is like, we want to prove that non-singular means A has an inverse. If A has an inverse, means the determinant of it cannot be a 0. Okay, so here we could actually like find out what is the expression for the determinant first. Okay, and we need to show that this expression here will never be a 0. Okay, so the most straightforward way for us to actually look at it is, because this is a quadratic, so we could actually like equate that to 0 and try to show that there is actually no values that k which makes this expression as a 0. So show that the b squared minus 4ac is actually less than 0 then. So it tells us that, okay, the determinant of a couldn't be a 0. Okay, so that the a that we have here is actually non-singular. Okay, we have got the BC. Okay, so here it's given that the CAB matrix will result in this thing. So we need to find the value of k. So basically, this is nothing much. It actually tests us about our operation, okay, on the multiplication of the matrices there. So no other thing that we could do. I mean, we just have to expand. Okay, when we actually expand, multiply everything, we just have to be careful. And after that, we compare with the value of the CAB given. Then we solve for the value of the k here. It's really nothing much for this one, just we have to be really careful. Okay. So whereas in the part C here is to find the equation of the invariant lines, okay, which is represented by the CAB. So you can notice, right, usually when they ask for the invariant lines, right, it will be about like through the origin. Okay, so it actually saves us a bit of the work to do. So anyway, we will always start with like the matrix multiplied by the xy is x prime y prime. So we multiply the left hand side for the matrix there, so we get 2 equations. And then because it's about the invariant line, so we will start with like the y prime is equals to mx prime. So try to relate the y prime is equals to mx prime. Other than that, okay, for the y, right, we know that they are actually mx. So the y will actually replace with the mx here. And then later on, okay, we should be able to get some nice quadratic, okay, which has which we still have got the x there, but we are actually not looking at the x here. Okay, we are looking at the quadratic here that we could actually like solve the quadratic and we get the values of the m. So the values of the m here are the are the gradient of the line. So not just like we find the value of the m there, yeah, okay, we need to list down the lines, yeah, so it is not just m here, okay, we need to actually list down the invariant lines. So substitute the values of the m back into the y equals to mx, okay, then only we will actually get these invariant lines here. Okay, so they didn't ask much about the transformation thingy, rather they actually ask more about the operations on the matrices. Okay. So let's look at the next question. Okay, polar. So this is a polar curve. It's r is equals to a tangent theta, where a is a positive constant and the theta is from 0 to 1 over 4 pi. Sketch C and state the greatest distance of a point on C from the pole. So if the question will have the sketch which comes first, it means this curve shouldn't be super difficult to sketch. In fact, it should be very easy. Easy in the sense that it should be monotonous, or it should be some usual trigo functions like sine and cos that we usually see. In this case, it's a tangent theta function, which is monotonous, as in when the theta goes from 0 to 1 over 4 pi, it will just keep increasing. Okay, in fact, when the theta is a 0, the r is a 0. So it will just start from the origin and then it will just keep increasing. And remember, this graph, right, it doesn't actually ask us to sketch until everything, yeah? You just have to be careful that, okay, the theta here is 0 to 1 over 4 pi only. So it's a good thing that we draw a line, which is about the theta is equal to 1 over 4 pi. Just draw some dotted line there to tell us that, okay, we can't go over that part. So we just have to like draw the graph which is like this. Just make sure that it is actually keep increasing for the r there. Okay, this is the how the graph looks like. 1 mark. Okay, this graph only worth 1 mark. State the greatest distance of a point of the C from the pole. So what is the greatest distance? So the greatest distance occur here when the theta is 1 over 4 pi. So when theta is 1 over 4 pi, so we have got the r is an a tangent 1 over 4 pi, which is a 1. So the greatest distance here is an a. So make sure you stick anywhere in the question here. Okay, the greatest distance is actually equals to a. Okay. For the second part here, find the exact value of the area of the region bounded by C and the half line, which is theta is equals to 1 over 4 pi. Nothing is super complicated. Basically, it's just to find the area. Okay, so nothing much that we need to consider. So it's the half r squared d theta, integrating from 0 to 1 over 4 pi. So when we actually square the r, we get a squared tangent squared. We could factorize out the a squared since it is just a coefficient. Tangent squared, we don't know how to integrate it unless we change it to some other identity, which is secant squared minus a 1. Okay, so only from here we know how to integrate a secant squared. It gives us a tangent, and then we have got like integrating a 1 gives us a theta there. After that, just sub in everything here and evaluate this area here, then we are actually getting this area. Okay, so for this one question, it is not so complicated like the previous paper that we have seen. Okay, next. Oh, okay. The next one is to actually like show that the C has the Cartesian equation. So it's to change from the polar to the Cartesian equation there. Okay, so what we actually have is basically from the r is equal to a tangent theta, we just want to try to create like the r cos and the r sine. So this is what we can see here, yeah. If we actually have like the tangent written as a sine over cos, so we move the cos over, so we have got the r cos already. But the right hand side here, it is still lack of an r for us to actually proceed. So what we do is we multiply by an extra r. Okay, so that right hand side is nice, we get a y. Left hand side, the r cos is an x, the r itself is the square root of the x squared plus a y squared. So in order for us to actually sort of like get rid of the square root there, we need to square both sides. Okay, so once we square both sides already, what we need to do here is just we try to make the y as a subject here. So we somehow get the y squared as a subject here. Okay, and just take the square root there. So we take so we get the y is equal to this expression here. Right? Okay. So this is the another part here. So using your answer to the part B, okay, deduce the exact value of like this 0 to half a sub 2 of like this x squared over square root of the a squared minus x squared. This is okay, we need to actually identify what is actually we have, okay, in the this value here. Because we actually realize that if we actually have got the theta here is a pi over 4, right? When we try to find the x and the y value, the x value is given by r cos theta. So we sub in the r and also the cos theta here, it gives us this, okay, 1 over 2 a sub 2. Okay, and also when we actually try to find the y, it gives us the same value as well. So if the curve can be actually looked at as like this Cartesian curve. Okay, so we are actually integrating from 0 to the half a sub 2. So this integral here is actually what we have here. This area here is actually the integral of the 0 to the half a sub 2 of the thing just now. So we want to find this. Okay, we want to find this thing here. So we know that this is a 0, this is a half a sub 2. So also we know that this y value here should be a half a sub 2 as well. So we want to find this area under the curve. So how do we actually find that? Because they say deduce. So deduce here means it should be something that is very easy for us to find, okay, from the previous part of the question. So that is, this area here is we are using the area of this triangle, having the base length of the half a sub 2, height also half a sub 2, to minus off with the area which is bounded by the polar curve just now. Okay, then we can get this area under the curve. So just minus from there. So this is the area of the triangle to minus the value that we have actually got from the first part there. The second part, sorry, okay, the area bounded by the curve. So this is, okay, we just have to carry out the, tidy up this a little bit. And when we actually get the answer, this is one of the possible expression that we could give. Okay, as long as it is in any equivalent form. Okay. So this is how we actually look at this question here. Okay. So let's look at the next one. Okay. Curve sketching. So usual thing, okay, we have got this equation and we need to find the equation of the asymptotes. Equation of the asymptotes is we do the long division. Okay, nothing much that we could do. Do the long division because this is an improper fraction. So we are actually getting this expression here after we do the long division. Then after that, we could already state what are the asymptotes. Oblique, which is from here. Vertical, which is we look at the denominator. So we get a 3/2 for this asymptote. Okay. So show that, okay, C has no turning point. Different ways that we could actually show that. Okay. I mean, we could do quotient rule, equate dy dx to 0, and show that it has no real solution. Okay, we can do that. But for myself, since I usually prefer to work with like the dy dx, which is like already in this form, right? It will actually gives us this one. And from there, I can actually try to conclude from that. Because here we have got the squared term, which is a negative squared term. So it will be actually less than 0. Okay, so some more, the dy dx has got a negative one. So it is like also like for the whole thing here, the dy dx is everything which is less than 0. So it means that this curve is always like decreasing. So from there, we can actually like prove that there is actually no turning point. Okay, so you could use some other way as well. Any logical explanation would do. Okay, but this is what I actually do. So you see, you can actually save a lot of the work without trying to do the quotient rule. It's very easy for us to make mistake for the quotient rule because there are so many things to differentiate. Okay, if you do this, then it's very simple and straightforward. Okay. So I guess the part C here is a sketching, yes. So stating the coordinates of the intersection of the axes. So you need to solve for the x-intercept and the y-intercept. So the space here is actually quite big lah. Okay, they give us the whole page to actually do that. So they actually expect us to have a bit of working here. Okay, because somehow we can actually do a bit of the working here. So they need to see the coordinates, yeah. So they need to see the coordinates of the turning point state there, or either that you just mark it on the graph. Okay, so you have got oblique asymptote, which doesn't look very nice, yeah, because it's a bit like sengit already. Okay, but you should actually use a ruler for that. So this is the oblique, vertical, and this is a curve that is like always decreasing because we already found out that okay, the dy dx just now is always decreasing. So if it is a decreasing curve, so the curve should actually looks like this. Because we are so used to the thing already, right? If the curve doesn't look like this, then it will actually look like this. Okay, but it is not the case. If the curve looks like this, means they have got turning point. But this one, they don't have turning point. So the curve should actually look like this. Okay, when you sketch curve, remember to mark, okay, all those important points here. Okay, this is what we get from the curve there. So the next one is to ask us to sketch the modulus curve. Okay, and hence find in exact form the set of values of x for which this modulus function is less than 4. Okay. What we actually need to do is we need to reflect, yeah. So we need to reflect this part up there, this part up there. Okay. So as we actually want to do the reflection there, right? Okay, this is actually the curve that we're actually getting from there. Okay, this is the the curve that we actually get from there. Okay, so another thing that we could actually also consider is that, okay, because these two parts of the curve, right, it is actually going near to this asymptote. So you see, okay, I'll show you. This is the asymptote, right? Okay, and this is also the asymptote, right? This part of the curve will actually go near to these two asymptotes here. For this part of the curve, it will actually go from sort of like from here, and then it will actually go to like this asymptote here. So supposingly, for an accurate curve, we need to like reflect this asymptote, and we need to sketch accordingly, like what we have in the asymptote there as well. In which, okay, we need to start here, right? So it should actually gives us this part of the curve here. Okay, supposingly it should work like that. Same to this one. This one, right, it is actually going near to the asymptote top at the top there, right? So supposingly, we should actually have the curve which is like this. Okay, we could we could reflect the asymptote at the top here to sort of give us a more accurate curve. But in the mark scheme, there is no requirement for us to show the reflected asymptote there. As long as it is reflected, the shape seems okay, then they will actually take it. Okay, the shape is okay as in, okay, this one is of course increasing like that, and we have got a sharp turn here. This part of the graph here, of course, it won't actually cross over the vertical asymptote, so it will just go near to the vertical asymptote. This is already considered enough in a mark scheme. Okay, so but of course, like I said, you could consider reflecting the asymptote as well for you to actually get a slightly more accurate curve from there. Okay, but like this is enough already. Okay, so the following part is the part that carries more marks, in fact. So we need to actually find out the value. Okay, set out the values of the x for which the value here is actually less than 4. So in fact, the 4 is actually here. Okay, the value 4 is actually here. So we know that we are going to find out these points here. Okay, so with that, right, we need to understand that, okay, they are points, okay, that is actually we are considering the positive of the modulus, and then another one is to consider the positive of the negative of the modulus there. Okay, because what happened was this is the reflected part, and this is the reflected part. So these two, we should actually use the modulus, the negative of the function equals to a 4, or we say the function is equals to a negative 4, in order for us to solve these 2 points here. Okay, for the original part here, this part and this part, we will actually get the equation when we actually solve the modulus is equals when we open up the modulus, it's equals to a 4. Okay, it will give us 2 different parts of the solution there. Okay, so usually for this kind of the question, right, because it's so difficult to design a very nice value, because this is like the latest stage already, it's very difficult to ensure there's a nice value. So sometimes you actually have got some ugly values there. So just bear with that, okay? Bear with that. You have got some very ugly values there, sometimes. So just bear with that. Okay. So these four values that we get from the two equations there are the values that it actually gives us for like these four. Okay, the four values here. This one, this one, this one, and also this one here. So okay, you just have to be careful of the values. You just have to like identify which value should be at which position there. Okay, later when you actually give the inequality, so you just have to look at the inequality very carefully here. So the inequality is in between this, and also between this and this, which is less than 4. Okay, the modulus graph is less than 4. So you just need to look at the values carefully there. Okay, and from there is to look at the graph and give the range of the values here. Okay, it is not really go and square both sides and solve. Yeah, no, yeah, it doesn't work that way. Yeah, you use the graph to actually solve it for this question here. All right. Okay. The last question here is actually a vector. So we have got two lines, okay, and then they tell us that okay, we have got a plane pi. The plane pi contains L1 and is parallel to the L2. Find the equation of the pi. Equation of plane, we need normal and a point. So we find the normal. So since the normal here, okay, we have got the plane contains an L1 and is parallel to the L2, we need to cross the two vectors which are parallel to the plane. So we need to take the direction of the L2 to cross with the direction of the L1 there. Because both of the vectors there, they are parallel to the plane. So you can cross them in order to actually give us a normal. Okay, so after that, we just need to use the r dot n is equals to a dot n. So the point A that we actually use here is a point for the L1 because the plane contains L1. So the most easiest point that we can get from L1 is this negative 5j there. So we just use that point. Okay, use the r dot n equals to a dot n, and they want us to give the equation of the plane here in this form. Okay, so we give it in that form here. Right? Okay, what is the next part? Okay, sorry, the puppy is down there. Find the distance between L2 and also the pi. This is an idea where if you have got a plane pi and L2 is actually parallel to it, so when we want to find the distance, it is just to find any point from the L2 and we just need to find the distance of it. Okay, so we use the formula. So take the point for the L2. L2 is this 4, 2, negative 2. Okay, the point. So we sub in the 4, 2, negative 2 to the equation of the plane. So for the equation of the plane, we need to do a bit of the work first. We move all the terms to the left-hand side, and we sub in the 4, 2, negative 2 inside the equation of the plane. That is actually our numerator already. Denominator is we find the magnitude of the normal to the plane. Okay, so with that, we can actually get this distance here. Okay, should be a very short working on it. So part C. This is like a super popular question that they really want to like to ask that because it can actually takes out a lot of the marks there. Okay, so it's a perpendicular. So point P on L1, point Q on L2, PQ is perpendicular to both L1 and L2. So what do we actually have from there is that, okay, this is P, this is like a Q like that. So it is actually perpendicular to both of them. The lines there, this is L1, this is L2. Okay, so we need to actually like find the PQ first because we know that the PQ is perpendicular to both L1 and L2. So with that, we've got the PQ, okay, P and the Q here. Before we know what exactly their position vector is, the P and the Q here, we will just take the coordinate or the position vectors here as the equation of the line. So they are just coming from the equation of the line there. Okay, so we find the PQ. So here the vector PQ is we use the OQ to minus the OP. This is what we get. Then we will carry out the dot product. PQ perpendicular to the L1. So we can use the PQ to dot with the direction of the line L1. It should give us a 0. So we will get one equation from there. Another equation is we use the vector PQ to dot with the L2, okay, the direction of the L2. Another equation. So from there, we're actually able to solve what is the value of the lambda and the mu here. Okay, so with the lambda that we have here, we can actually state what is the position vector of the OP already, because OP is in terms of the lambda here. Okay, so we just sub in the lambda, so that is why it gives us like the value which is not that nice there. Okay, and after that, okay, we need to give an equation of the line PQ. So the line PQ here is, it passes through P and Q. So maybe we will just use the point P as like the point that the line passes through. To get this Q here, what we need to do is just we need to sub in, okay, the value of the lambda and the mu back into the these L1 and the L2 here. Okay, we can sub the value inside here, or okay, there's an or here, or we can use the normal. Okay, the normal that we actually have here is the direction of the PQ. Okay, we just need to recall the idea. What happened when we actually cross two vectors? So when we cross two vectors, it gives us a vector that is perpendicular to both the vectors that we were crossing. So if we cross the direction of the L1 with the L2, it will give us this vector, which is perpendicular to these two lines here. And then PQ is also perpendicular to these two lines here. So the direction of the PQ, we could just take it from the normal that we have just now. Okay, so we just take this normal and we actually become the direction of the line PQ already. Okay, of course you will still get the same thing like I said, when you try to solve the mu and then you sub into the PQ just now, you get the similar thing. It might be a multiple of the normal. Okay, so this is how we actually get the equation of the line here. Right? Okay, yeah, so that is all for this paper here. So I mean this you know lah, okay, these vector questions, right, they really like to ask one. So make sure you really know how to do it because it carries a lot of the mark. In the recent past year, it's even more. They actually have like 10 marks for this question here. So it's actually quite a lot. Right? So make sure you really need to like know how to actually do this question here. Okay, it's very routine. Right? Okay,